was expecting no one to know what AHV really is. So I'm one of the engineering leads at Nutanix, and I work in the Acropolis Hypervisor, which is our KVM QEMU-based offering. And I'm here today to talk a lot about storage performance and virtualization, and what we're looking at doing with SPDK and NVMe drives. And I'd like to start by highlighting some key events over time that brought us where we are today. And today, a lot of people just take for granted how we run virtual machines, right? We can run Linux, Windows, BC, whatever you want on computers like our laptops, and it just works. But back in 2000, there was a big desire for this type of workload where we could decouple software and hardware and run virtual machines in any servers in our data centers. But the only way we could really virtualize OSs was by doing binary translation, which was very expensive. And around 2003, in the University of Cambridge in the UK, a group of students started the Xen project. And what they did was basically modify operating systems so that they could run natively on the CPUs without binary translation. And that showed that virtual machines could really run decoupled from hardware. You could have things like live migration, etc. And it just worked. It was amazing. But you had to modify the OSs. So running other workloads like Windows was a bit harder. And there was so much interest in the technology that Intel and AMD a few years later modified the way x86 worked so that they could offer virtualization extensions. And today, any CPU you care about will have virtualization extensions. And that allowed operating systems to be virtualized without any modification. And CPU-bound workloads would run at amazing performance, and that's what everyone does today. But the story for I/O workload was a little bit different. There was always some sort of undesirable overhead. And a few years later, the Intel and AMD introduced again something called the IOMMU, which allowed things like PCI pass-through to happen. So that's when you do, you may know this technology as VTD, and that's what allows PCI devices to be completely passed through to virtual machines. And the performance of that is obviously great, but you lose the decoupling that you wanted between software and hardware. Now your virtual machines can't really move that much. And to aggravate this, NVMe drives hit the market a few years later. And I don't know if you're familiar with that. I have some timelines on NVMe if you want to talk about that later. They're basically very, very fast drives. And a lot of people think that because they're very fast drives, that performance is no longer a problem. And as we're going to see during this presentation, that's actually quite the contrary. The faster the drives, the harder it is to virtualize them. And that brings us to a few years later. It was actually 2015, I checked, and it was December the 28th. On December 15, I don't know who was working there, that the SPDK project was launched. If you haven't heard that, that's called Storage Performance Development Kit, and it's an Intel open source project based on the same ideas of DPDK, which is meant for networking, and it allows NVMe devices to be driven from user space, cutting the kernel completely out of the picture. And we're going to talk about how that is being used, or how we're planning on using that for virtualization. Before I get started, I have a little disclaimer for you all to read. One of those things that tells you not to buy anything from Nutanix based on what I'm talking today. This talk is full of forward-looking statements and results from prototypes, and there's absolutely no commitment to release anything that we're discussing here. Yeah, and I've organized this talk by talking a lot about storage performance. I'd like everyone to come out of this room a complete expert in the topic, and we're going to do that as we talk about hypervisors and we look a little bit into hypervisor architecture and where bottlenecks are and things like that. And then I'm going to talk about a little bit about AHV and SPDK and how we're using that for a user space stack that provides amazing performance, and brings us to a world where we can actually have millions and millions of IOPS on a single virtual disk, which is something very difficult, and to the best of my knowledge, there isn't really a hypervisor out there that can do that. So let's start by looking at what a storage data path looks like. And you can imagine there's some hardware here with your physical devices, and there's some OS, and you have some workload running there. This could be an application, it could be some benchmark to whatever you want. If that wants to get to that drive, you would normally make system calls and go through the kernel. That's obviously a very simplified version of it. If you are interested in a more complete version of it, you can look at the Thomas Cran diagram for the Linux storage stack. I actually highly recommend a reading of that. If it looks complicated and difficult, it's probably because it is complicated and difficult. But it's very enlightening, and we may make references to that as we go along. So in terms of performance, we can start thinking about where we spend time when we're processing these requests. And traditionally, especially for mechanical drives, the order of magnitude for times for the time you spent on the disk itself is in the order of milliseconds. So we're talking about, let's give an example here, 10, 20 milliseconds, right? And the amount of time you spend on software is probably in the order of microseconds. We can also give a time here and say 5 microseconds. So traditionally, operating systems would actually hold requests back and not give them to the devices straight away. Because if more requests came in, they could reorder them, maybe glue them together, modify them in a way that will help this device to perform better. That's largely done by elevator schedulers, as Paulo knows. And you can imagine that when you put a hypervisor in the middle, then depending what kind of virtualization you're doing for the storage, all of the access to this drive actually has to go through some more software, which perhaps add another 5 microseconds. So no one really cared if before you spent 20.005 microseconds and now you spend 20.01 microseconds. It's pretty much the same, right? Now, when you replace that with NVMe drives, and especially NVMe drives with media like 3D Crosspoint, if you haven't heard of that, that's a different type of flash memory that Intel and Micron developed, and they put that on NVMe drives, and the media is so fast that PCIe itself becomes a bottleneck at that point. Then this drive responds in 5 microseconds. And now you care if that's 5 plus 5, that just doubled your latency, and plus 5 here, it tripled it. And that's why the virtualizing normally aggravates your situation, especially for fast drives like that. So I have to be pointing here, I think. What are we really measuring? There's 3 storage metrics that we should all know. And the first is the simplest of that is throughput, right? Everyone knows about throughput. If you downloaded a file off the internet, you've seen something coming down in megabytes a second, you can associate that with moving a volume of data over some amount of time. And the other is IOPS. And unless you are in the storage business, you probably don't care so much about this, but it basically measures how many requests you can complete a second. And lastly, we have latency, which measures the amount of time that a request takes to complete. So take a moment to look at these 3 metrics and just think that throughput actually measures the amount of data over time. IOPS measure requests which have some amount of data associated with them over time, and latency measures the amount of time it takes to transfer some data. So the question is, are they really measuring the same thing? And why do we have 3 metrics? And yeah, they are actually measuring the same thing, more or less, right? We're basically stressing the system differently and measuring how the system responds when they are stressed in different ways. I love making analogies, and one analogy I have for this is measuring the performance of a car. What does it mean for a car to be fast? Is it top speed or is it acceleration, right? It's a combination. And another example I like to use is if you think of a runner, right? What does it mean to be fast for a runner? Is it having very long legs and doing very long steps? Or is it to give very fast steps, right? In the little jingle there. And it probably depends, right? It depends on the rules of your race. Maybe if the rule is that you have to keep a foot on the floor at all times, then it matters that you can give very fast steps, right? And as far as hypervisors go, we're probably interested in both. We're interested in having lots of legs. We're interested in running really fast by moving those legs really quickly, and perhaps those legs should be really long as well. And this is really difficult to achieve when you're implementing a hypervisor, and that's why all of those hypervisors behave differently today, because you can imagine that if you have to allocate memory on the hypervisor to process those requests, and then when they're done you free them, then your performance is not going to be great because you're allocating memory and freeing them all the time. If you pre-allocate a bunch of memory for it, then maybe you're going to waste a lot of memory if your workload is only does the small requests, and now you're affecting things like the density of virtual machines you can have on top of your hypervisor. So all of this come into play, and it's really difficult to find that balance. Some hypervisors actually need to copy the data around. They bounce memory, which is obviously terrible. And there are basically two ways that you can drive load in a device when I talk about pushing the drive in different ways, right? And one of them is by issuing larger requests. And another one is by issuing a larger number of requests. And a lot of people think that when I was talking about those metrics before, a lot of people think, oh, throughput is used to measure sequential workloads, and IOPS is used to measure random workloads. And while that is not wrong, it's also not right. It's not a complete picture of this. And it has all to do with the workload and how your data is laid out. If you think of Netflix, for example, what does a workload look like? They have large movies, and they have to stream it off the internet. So they have to read that from the disk. They know exactly where the data is, and the data is probably laid out contiguously. So they can afford to do very large requests, or at least very large read requests, so they can then shove that off the network, right? And that's why what they care about is moving large volumes of data, which associates with throughput. And it's not a necessity, but it's kind of how they pair together. A different example would be a bank, for example, and they have a database, and they're serving statements to their customers. Now you have customers, millions of customers requesting the statements, and that hits a database, and the database has all these requests coming in, and they have to read some indices on their tables in disk, and then reading the data, and then reading it back, and those requests are probably smaller, and they're probably all over the place. So what you care about in that case is the time it takes to complete each one of those requests, and also how many of those requests you can sustain in flight at a time. And this also ties back to hypervisor implementation, because different hypervisors have, when they either reserve memory beforehand or as they allocate more memory, they have different implications in how many requests they actually support in flight, right? What the size of their I/O rings, if you want to think in those terms, or how large are the requests they support. So that's why this association normally happens. So let's start with some graphs and talking about some real data. What I'm showing you here is the completion latency graph for a mechanical drive. And what I'm doing is pushing this drive by submitting larger requests, but always one request at a time. My queue depth is 1. And the x-axis has the request size in logarithmic scale, so I start with a single 512 byte sector, and then I keep doubling that all the way to 2 megabytes. And on the y-axis, I look at the completion latency, also in logarithmic scale, in microseconds. So you see that even for a mechanical drive, very small requests complete in about 50 microseconds, which isn't really that bad. And another interesting thing you notice is that it doesn't really matter if I'm reading a sector or if I'm reading 4 kilobytes, maybe even 8. The completion latency is almost the same, which means your performance is better if you can afford to do 8 kilobyte requests compared to 512 byte requests, at least in terms of throughput. And then something really interesting happens. And I don't know how wavy this screen is, but that is actually a straight line. And this suggests that the storage at that point is completely saturated. So when I double the request size, the time to complete that also doubles. And this is perhaps easier to see on a throughput graph. So on a throughput graph, what we have is same x-axis, log scale and request size. But on the y-axis, I have throughput, now in linear scale and in megabytes a second. And you can see exactly that as I double my request size in the beginning, my throughput increases drastically up to a point where the drive is saturated, and then the performance just stays the same, right? It doesn't change, and that looks like about 115 megabytes a second, which if we refer to the data sheet of this drive is about what it should do. I hope that all makes sense. And here's my first $1 million question. I don't know if I have t-shirts giveaway, it doesn't matter. I have so much content that I'd rather we hold discussions to the end. What happens if I virtualize this drive and try to do the same workload from a virtual machine? So what I'm going to do here is use QEMU 2.6, run a Debian virtual machine, and present this entire disk as a virtio-scsi device to the VM. So the VM sees, let's imagine SDB in the Linux, and the requests, the raw requests on that device would just be interpreted by QEMU and then passed down to the real disk with libio. And that's what the performance looked like. So this is probably the most important kind of graph you can draw to understand virtualization overhead. Remember what I said before about if it was 20 milliseconds, no one cared, but if it's 5 microseconds, you care. This drive was responding in the order of 50 microseconds for small requests. That's what's happening there between a sector and maybe 8K, 16K. The drive responds so fast that the overhead of the hypervisor is very noticeable. However, when the drive is saturated and it's taking milliseconds to respond, then the overhead of the hypervisor disappears. So this is why, and the lines meet on the top, you get the same 115 megabytes a second. And this is why you may find customers that say, oh, for my workload, this hypervisor is not great. Let's say I'm doing 4K random reads and I was getting 60-something megabytes a second, and I move this to a VM and now I get 40 megabytes a second. That's a big drop. But other people who can afford to do larger requests, like in our example, Netflix. By the way, I'm not claiming to know how Netflix works or anything like that. I'm just picking that as a simple example. Then maybe they see no overhead. What is the difference with an NVMe drive? So this is that same latency graph, but using an Optane drive by Intel, which has NVMe. It's an NVMe drive with 3D cross-point media. The first thing you notice is that even at 2 megabyte requests, that's still under a millisecond, where the other drive was a lot more than that. A few orders of magnitude bigger than that. The other thing you notice is that completion latency is under 10 microseconds here. And based on what we know of this drive, this is probably 5 in the drive and another 5 or 6 in the drive and another 3 or 4 in the OS, right? That's just a bare metal measurement. The other thing you might notice is that the drive is not really saturated, right? If you try to put a line there, no matter how you try it, it doesn't really look like it's saturated. And I have another great analogy to explain this drive, which is you can think of the CPU that is submitting I/O to this drive as a fuel pump in your car. And you can think of the drive as an engine. And NVMe drives are engines that have lots of cylinders. So here we're submitting one request at a time, which means my fuel pump is just throwing petrol in one cylinder. And the request size is the amount of petrol, maybe the pressure, that it puts inside that cylinder, which causes a bigger combustion. This engine is so powerful, and this cylinder is so powerful, to the lack of a better word, that it doesn't matter how many fuel you throw there. If you're throwing fuel in just one cylinder, up to that reasonable number, it doesn't really get you much better performance. I mean, it's huge performance. It's just, it could potentially be better. And we can see that on the throughput graph, right? On the throughput graph, the other thing you notice that this drive is doing nearly 2.5 gigabytes a second. And I know that this drive should do more than that. It should do about 2.7. So we haven't really saturated the drive yet in terms of throughput. And the other thing you notice is that this throughput S-curve, as I call it, is not really flattened out at the top, right? So what we can do to push this drive better is actually get our little fuel pump and put fuel in 2 cylinders. So I'm going to bump my queue depth from 1 to 2, and now you see that the performance goes up, the throughput goes up, and now we have a flattened point on the top, and it's also what we expect to see from this drive, about 2.7-ish gigabytes a second, right? So now it makes sense, and you see that these drives are really highly parallel. And I have some more data to explain that later, what happens when actually doing I/O in parallel on this drive. So for the second $1 million question, what happens when we move this to a virtual machine? And well, that's disappointing. So now you have one CPU in the virtual machine doing I/O on that virtio-scsi drive, and then QEMU picking that and sending to the drive, but the performance is not even matching what you get with a single CPU on the host in bare metal. And you say, okay, but we can get the VM and send 2 I/Os as well, right? Two I/Os in parallel for the VM. You can. And now the throughput gets a lot better, right? As a matter of fact, with requests of at least 256K, you actually get the full throughput out of this. But think about this again for a second from a customer point of view, right? If you are your streaming service and you're doing 256K or 512K requests, you notice no overhead. You can get 2.7 gigabytes a second. What about the guy that is doing 32 kilobyte requests? On bare metal, he was getting 2.6 or so gigabytes a second. On the virtual machine, he's getting less than 1. That's a huge overhead, right? And this is also why it's so important when you do any performance measurements of the kind to be very comprehensive on what you're measuring. Experiment with all queue depth. Go from 1 all the way to 256 if you have to, or more. Experiment with different number of CPUs submitting I/O. As we're going to see now, that makes a big difference. And different request size. Figure out how to visualize this data in a way that it can meaningfully show when you have and when you do not have overhead, and what this overhead is. If you don't measure all these points, you don't know what's going on. So I've been saying that these NVMe drives are highly parallel. They're like an engine with many cylinders. And one way of looking at this is, if we think of time here, the CPU submitting some I/O to the storage drive, and that's the blue box there. Then the drive is working, the CPU is idle. When the drive completes the request, the CPU works a bit and submits another request to the drive, right? So what we're doing here with this previous example is using this CPU to submit 2 requests. And what happens now is your CPU is busy submitting the first request, then it's busy again submitting the second request. And I'm highlighting this because I/O stat can be a little bit misleading if you're looking at that. I/O stat is telling you that this drive is 100% utilized, but this drive is not 100% saturated. And this graph suggests that because the latency to complete this request is the same. And as a matter of fact, you could keep submitting more and more requests in parallel, and the latency doesn't change up to some point. And you're going to get to a point where on this type of drive that is really, really fast and highly parallel, you're going to fully utilize your CPU, and the drives is still like having a lot of breathing space, right? Have cylinders that are not even using. You can imagine that your fuel pump is like filling a cylinder, filling a cylinder, filling a cylinder, filling a cylinder, and the first cylinder exploded, and you're still filling cylinders, right? So by the time you get back there, the storage had more power to give. And this is really easy to see when we measure IOPS, right? And this is an IOPS graph now. And what I have on my x-axis is my variable of interest now is my effective queue depth, which is how many requests I'm actually putting out to this drive at any one time. And linear now from 0 to 32. I'm only measuring 32 because 3D cross-point drives are so fast that they actually saturate with a small queue depth. You don't really need to measure all the way to something like 128, at least in these examples. And on my y-axis, I have what I'm getting of the drive in thousands of IOPS. So you see that with one CPU, the performance of 1 outstanding request, 2 outstanding requests, 3 outstanding requests pretty much grows linearly. With 4 outstanding requests, curiously, it's better than linear, and I can explain later if you want. But at some point, it flattens out. This is the point where the CPU saturates and not the drive. And we know that because based on the data sheet of the drive, we know we should be doing 600,000 IOPS. So we take a second CPU. Let's put another fuel pump in, and let's submit requests at the same time from 2 CPUs. And this is where things like the block multi-queue really come into play, because now I can submit requests in parallel from multiple CPUs without any contention on the request queues. I don't have to lock them. That's what block multi-queue gives us. And with 2 CPUs, yeah, we do get to peak performance of the drive, right? On this type of drive, with something as low as queue depth, apparently 10 or so, 8 maybe, we can get 600,000 IOPS, right? That's a really fast drive. Now for the $3 million question, what do you think happens now from a virtual machine? And now we're CPU bound, so things are different, right? And yeah, you're right. The performance for one CPU in the VM is really poor. And you may say, okay, but we can put more CPUs in the VM to get better performance, right? No. So you can try 2, 3, 4, 5 CPUs in the VM and nothing changes, a little bit. But look at this customer now, that on bare metal, he used 2 CPUs to get 600,000 IOPS. Now he's in his VM pushing 5, and he couldn't get past 200. And so you see how the story is getting worse. And I hope that ties back to my timeline of why NVMe made things a lot harder for hypervisor developers. And if we look at the architecture of this hypervisor, that may become evident what's going on. And on the top here, I have my virtual machine with the software simplified. So there's storage workload talking to my virtio-scsi driver. And I'm talking to a virtual controller that is backed by QEMU. And QEMU is then using libio to get to this drive. Now, the problem is that QEMU only has one thread to handle all I/O for the VM. So it doesn't matter how many virtual disks you add to this VM. It doesn't matter how many controllers you add to this VM. That all goes to that one thread. Now, I've learned last week that recently QEMU managed to finally, after I think 3 or 4 years in development, get storage data plane working. And that means you actually get an I/O thread per controller. So maybe adding more controllers would help, because then you can use more CPUs on the hypervisor side, right? Right now you're bottlenecking on that thread there. Other hypervisors like XenServer behaves a lot differently. So XenServer has a completely different model, and what they do is that on the host side, it's not really a host, they call it a control domain or a driver domain, the thing that's handling the storage, we have a tap disk project, a tap disk process for each virtual block drive that is presented to the VM. So the VM doesn't really see a SCSI controller, it sees block devices, which is Xen specific. And now you could actually scale by adding more virtual disks. However, tap disk is really bad at handling I/O. The Xen protocol originally only allows 32 outstanding requests per ring, only allows one ring, and each request can have a maximum of 44K. So you can imagine that you can't really get a lot of data in flight. And then you have to resort to things like indirect descriptors that were not properly thought through, I think, at the time when it was designed. They were not taking this kind of thing into consideration. And the other problem you have is that this is not how you should be scaling your storage for a VM. Right? Think that you have a powerful database VM with 128 vCPUs, I don't know, 64 vCPUs, depends on your box, yeah? What you're going to do to get storage performance, you're going to add 100 virtual disks to this VM. Each one of these guys only do a few dozen, 1,000 IOPS, right? So you're going to run out of physical CPU in your box before you run out of, before you get peak performance for a single NVMe drive. And, oh, it crashed. And this is not my laptop. It's a different version of it. I'm sure you can pick up where it stopped. Don't panic about the number of slides. This is just a bunch of support slides in the end. We can jump to AHV, which is our hypervisor based on QEMU and KVM, so it looks a lot like what the QEMU one looked like, with the difference that our QEMU used to talk iSCSI via libiSCSI to a software-defined storage backend. So the data path is a little bit longer. And when we started shipping platforms with SSDs and NVMEs, we had the same problem that QEMU started to show its limitations with the single thread handling the I/O. So we wrote a mechanism which is upstream in QEMU called vhost uses SCSI, and it allows the virtio-scsi data path of a VM to be offloaded to a separate project or a separate process in user space, and we call that Frodo. And you can think that, if you're curious about the name, you can think that drivers have I/O rings, right? You know, who carries rings? And the real name comes from facsimile relay of data path operations, obviously. And the idea is that because we're doing iSCSI and we have a software controller that talks SCSI, what Frodo does is just grabs the SCSI commands from the VMs and put an iSCSI header and ship them off without having to do anything with the packets. And we were very thoughtful when we considered things like memory allocation, how much memory you need to allocate for a certain VM, etc., which made it very lean. And out of the box, it provided double the IOPS performance that we had with QEMU. And most importantly, Frodo was actually multi-threaded. And the reason we got to do this quite easily is because we started presenting a multi-queue SCSI controller to the guest. So if your guest is using block multi-queue and SCSI multi-queue, you can benefit of all the advantages that multi-queue gives you, like a lock-free data path, and also a really interesting aspect for scalability, which is if you need to put more requests in flight, all you have to do is put more CPUs in your VM, because then you're going to get more harder request queues, which are really virtual. So the controller we expose is going to have a request queue per vCPU for these guests. Now we're scaling correctly, right? If you think that you have a big database VM, which has 64 vCPUs, each CPU gets a hardware queue, and each one of those queues can support 128 requests. So that's a lot better already. But we still have a problem, which is we still have to go through iSCSI, and that is showing some grief with NVMe drives, where we're trying to figure out how we can shorten the data path. I'm not going to go into details of how we can separate our control and data plane to get that, because that's out of the scope. But we're basically looking at a way of getting Frodo to talk to drives directly. And an interesting point around that is that, waiting on time, yeah, I'm probably okay. Is that we measure what happens when you go through libio, block layer, and NVMe drivers, and the kernel one. That's where SPDK comes in. SPDK is a project that allows a user space process to own a piece of hardware, in this case an NVMe controller. And you may say, oh, but if you use that, I can only have one process using this drive. Well, I've got news for you. This is a hypervisor. We are the only process using this drive. So we can link SPDK with Frodo and talk to the drive without going to the kernel. Why is the kernel there? The kernel is there to allow pieces of hardware to be, amongst other things, be shared with user space applications. So you can think that a network card is shared through any application that it wants via socket APIs, etc. And perhaps storage devices via file systems, etc. And we don't need that. We're the only user of the drive. We can put any data format we want here, and we can just control this device straight away. SPDK has the also the extra advantage of not requiring interrupts back from this device. Now you saw from those graphs that if you have queue depth 3 or 4, you already saturated the CPU. Any real workload is probably going to do more than that, especially if you have a number of virtual machines running here doing I/O on the storage. So what you do is you submit the request to this drive, and then you poll on the completion queues of this drive without actually waiting for an interrupt to signal you that a request completed. You say, here's some I/O. Hey, are you done yet? Are you done yet? Are you done yet? Until it comes back, right? And this is the results that we got from this experiment. What I'm showing you here is the IOPS graph with the comparison of the purple line being the 2 CPUs bare metal via the kernel, and that being the 2 CPUs in RVM going through QEMU, which has a single thread, going to the drive through the kernel too. And the VM has the aggravated point of also going through its own kernel, which is virtio-scsi. And that means a request goes, if you refer back to that Thomas Krun very simple diagram, you see that you go to the block layer, then you have to go to this SCSI layer before you get to that driver. And that adds a lot of latency to the request itself. And it's not just the latency that increases. You have to remember that if you're spending more time in software, you saturate your CPUs sooner, right? That's one of the reasons why this is saturated so quickly at less than 200,000 IOPS. And when we tried our Frodo with SPDK, the first thing we noticed is that even for one CPU in the gas, the performance was already a lot better. And then it matched what we were getting at the peak of QEMU before. And we identified this to being a bottleneck in a single gas CPU. And even using only one CPU in the hypervisor, we didn't even need to be multi-threaded. We could actually add a second CPU from the VM, and that already doubled the IOPS. And if you bump 3, 4, 5 CPUs in the VM doing I/O, we can actually get to 600,000 IOPS, which previously was not possible at all. Again, this is just on top of a single virtual disk. And the guest here is also using multi-queue, right? But going through to this SCSI multi-queue stack. So there is an overhead, right? If you look at the purple line to the top blue line there, there's still measurable overheads that we're trying to eliminate. And then we refer back to this, and we said, well, okay, so if our bottleneck is now the guest's kernel doing virtio-scsi, what if we can do something different? So we don't want to break our existing customers, so we're not going to stop supporting virtio-scsi, but we're also looking at how to emulate NVMe drives outside of QEMU. That's a discussion that's currently going on the developer mailing lists. And one thing that people can do right away, and they don't realize, is they actually can use SPDK in the guest. So SPDK, apart from driving NVMe devices, it can also drive virtio-scsi, virtio-block, and some other things. So now what you have, for the first time again ever, is a full user space data path from a virtual machine all the way to the physical device. You have a user space application that is allocating some memory, registering that with a virtio-scsi controller. And then when it puts a request on the I/O rings, Frodo, which is spinning on all the guests' submission queues, will pick that straight away without having to be kicked by a guest. And then it can submit that down to the device and ring a doorbell on the device, obviously. The device will process that, and Frodo will pick up the completion as soon as it's ready, give it to the VM as soon as it can, and the VM, which is using SPDK, it's also spinning on its completion queues, on its virtio-scsi completion queues, right? And then it can actually pick up the completion straight away. So we're cutting down a lot of latency, and we're cutting down a lot of work that we don't really need to do, right? Which is transversing the kernel here and transversing the kernel there. And check out what happens. What I'm showing again is the best of the world as we have so far, which is two CPUs on bare metal using libIO through the kernel, and 5 CPUs on a virtual machine on top of a hypervisor that's using SPDK. But the light blue line is the VM still using the kernel. So when I try one CPU in the guest using SPDK and one CPU in a hypervisor using SPDK, the performance is actually better than what I had in bare metal. So for very low queue depths, we're already having insane IOPS rates. You can think that queue depth 1, it's like 120 or something thousand IOPS, right? This is really fast. And we can saturate this drive with a single CPU in the guest and something as small as queue depth 8. Now, the cunning observer will tell me that's an unfair comparison because you're comparing to bare metal where you're using the kernel. And I actually got that question once. So I said, fair enough, I'll go and measure bare metal using SPDK directly on the drive, just to get an idea of how much overhead we have now. And that's the red line there. So bare metal on SPDK, with SPDK to an NVMe drive versus a VM with SPDK on top of a virtual controller, it's tiny. This is so tiny, I'm prepared to claim this is almost zero overhead. Right? There is absolutely no workloads out there that I can think of that are going to perceive any virtualization overhead here. And you may think that maybe we're burning too much CPU because SPDK spins a lot. I'm going to prove to you this is a misconception, and do not let anyone tell you otherwise. So to give some numbers on this, this current prototype we're measuring is actually adding about 700 nanoseconds overhead on a request, which is almost nothing, at least until we get the new class of storage devices, right? And we're noticing that discussing the gas is becoming a bottleneck. And what I was just telling you about is that people think that SPDK burns CPUs. But actually, SPDK is a lot more efficient than you imagine. Think that through the kernel, not only the performance is lower, but if I have something like queue depth 4, I'm already burning the entire core. So just burn the core anyway, right? And what is better, even by just by burning one core, you can actually get much higher IOPS anyway. You get much more value for your money, right? And the same thing goes for VMs. And this model actually enables something that I'm going to talk about later, which makes virtualization an attractive option, even if you don't really need it. But before I get there, let me try to give some easier graphs that perhaps you want to use in the future. And I find that even the non-technical people, when I talk to them about this, that's something they can very easily understand because there's stuff catching on fire. And as I said, the kernel with queue depth 5 or so did 350,000 IOPS and it burned a CPU. SPDK, and by the way, this is 4 drives now. I forgot to mention that. So I took 4 of these Optane drives. It was everything I could get my hands on. Maybe I get some more soon, and if they fit in the box, we can try some extra. But now we're talking about 600,000 IOPS per drive, which is 2.4 million IOPS, right? And SPDK with a single core and as low as queue depth 5 per drive managed to get to 2.4 million IOPS. So you're using one CPU there, and you're getting peak performance out of 4 drives. So you ask, oh, but the kernel can get there too. I just need to put some more CPUs to work. True. You actually need 10 cores being used full on to get to the same level of performance, and you need 3 times more requests in flight to actually compensate for that. So I hope this shows there's no argument that SPDK is more efficient than the kernel, especially as you're trying to get the full power of your drives. And also at lower queue depths. So we can see how that relates to virtualization again, and you can imagine what can our prototypes do. And they can actually get to the same 2.4 million IOPS using 2 threads on the hypervisor, and we need a little bit more queue depth than you would need on bare metal, which is about a 32, which is like 8 per drive or so. And we can actually take this, and we do that test, and present it to the VM as one disk. So you can have a virtual machine that has 1 virtual disk, and it can do 2.4 million IOPS on that 1 virtual disk by combining more NVMe drives. Now, in reality, workloads probably don't want to do that because they want to have some sort of resiliency on their data, or perhaps they want thin provisioning or compression or deduplication. And that means the hypervisor will be doing something with the workload, maybe replicating that to another node in the cases of hyperconverged systems like ours. So unless you have temporary disks, that's probably not what we're going to be using, scratch space. But if you have scratch spaces, and this is particularly relevant for power users, people that perhaps are doing CAD workloads, and they want to have some scratch space for temporary access, or they're doing some computation, they need disk space for temporary things, and if their application crashes, they don't care about losing the data, that can work for them, right? That's the kind of performance they're realistically looking at. So before I wrap up, I'm back to what I said in the first place. The faster the storage, the harder it is to virtualize it. It's not that the devices are fast and we don't have performance problems anymore. And the time you spend on CPU is really important, and we have to be very thoughtful about how we're using what we're doing. Even small things like jumping to a driver is relevant now. And I actually have some data, if you're interested, in a comparison between FIO, which is this famous benchmarking tool, and Intel's PERF, which is benchmarking tool written exclusively for things like NVMe drives. And it actually can show that FIO bottlenecks because it's doing too much time stamping and other things compared to a more lean benchmarking tool. And that until we have a better story with storage offload technologies, and you may have heard of the new kids on the blocks like SmartNICs and things like that, and there's a lot of discussion going on now with SmartNICs manufacturers about how they can actually create a hardware solution that can help with this. But for the time being, a user space stack is definitely the way to go. And I mentioned that you may actually want a hypervisor even if you don't need one. And some of the reasons, one I've already mentioned, is you can get multiple drives and actually combine them in a single virtual disk, which can be very advantageous. But you also can benefit from the following scenario, which is easy to overlook. You can have a hypervisor with SPDK driving this local drive or sets of drives, and you can have a virtual machine that may or may not use SPDK to talk to the virtual drive. Maybe some applications in the virtual machine once use SPDK and others don't. You can actually split this drive by presenting two separate controllers to the virtual machine, and one application of the virtual machine can use SPDK in one of them, but use the normal kernel data path for the other. Or you can run two virtual machines and separate it in that way too. And then the only problems you're left with is how you're going to deal with fairness and things like that from the hypervisor side between people who are doing a lot of I/O and not. And BFQ, as you watched yesterday, may probably help with that, or at least with those ideas. So to wrap up, I think that if storage devices keep getting faster and faster, that may be challenging for a lot of people out there. But I would like to think that with this kind of idea, we're ready for devices as fast as they come. And with that, I'll say thank you and take any questions that you have.
In real storage, you will have metadata on the storage devices, which should be read and updated from the system. So this will reduce effect of adding more cores and more queues.
So the question is around what do we do with extra metadata. So in all of these examples I've used, I've been doing I/O on top of raw devices. And an interesting and a very valid question is how do we actually organize virtual disks on these drives, and what do we do with metadata if we are not using a file system? SPDK implements a number of logical layers inside of its stack. And they offer logical volumes, and there is even something that looks like a file system, but it isn't a full file system as you would expect it. But you can use that to organize the data in disk. And virtual machines, if they are going through the kernel, they can just use normal file systems there. And then we're back to the numbers we had when we do not use SPDK in the guest. But for the hypervisor side, the solution is usually for applications like Frodo or other applications that link into SPDK to control the data format themselves. And an interesting point that you also raised is, isn't managing more metadata becomes more expensive? For the logical volume support that SPDK does, this has been measured to be neglectable. So it's very, very low. And interestingly, just a few weeks ago at the SPDK Developer Summit, I heard them presenting that they are adding support for features like compression on SPDK. And what they are doing with the metadata is storing them on Optane memory, which is persistent memory in the format of DIMMs. Since they are byte addressable and they have much lower latency. So SPDK can actually use PMDK. They really like those kind of names, don't they? To store the metadata on persistent RAM for the drives. And whether that's a good idea or not is a separate discussion. But there are a number of what you're raising is a very valid problem, and there's a number of people coming up with solutions. We're coming up with our own format for data storage on for logical volume management on these drives. We don't expect it to have significant performance impact if it's thought through correctly.
How many megabytes you're writing and what kind of data you're writing? Just zeros or something else?
This is all random data. So all FIO and PERF are configured to work with complete random data when they write to this. So the way these benchmarks work is they pre-allocate some buffers and they fill it with arbitrary data and then they write them to disk, right? So beforehand. And then the workloads I was showing you was sequential or random reads, which essentially is reading random data. So there's no caching involved. And also, since I'm doing this without going through block or the page cache or anything like that, there's no caching going on at all. Thank you.
Thank you for your talk. I have a question. Whether you tried to pass mediated devices?
That's a really good question. So the mediated device story is coming in for how we can get an NVMe drive out of QEMU. So the way the mediated core works in the kernel is basically a mechanism for a driver to register a device with that, which can then be looped back via VFIO to a VFIO user, in this example, QEMU or SPDK. And the problem we're having is how do we extract this virtual NVMe device that's being presented to a virtual machine out of QEMU. And that's where MDEV comes in. One way of doing that is to load fake kernel driver. And I'm saying fake because it's not really driving any physical device. This driver registers a PCI device with the mediated core. And this driver talks back to user space to an application that can then emulate the NVMe drive and probably uses SPDK to talk either to local drives with an NVMe or remote drives with NVMe over fabrics over perhaps our DMA. And that's one way of doing it. The other way of doing it is just getting QEMU to offload PCI devices directly. There are patches on the mail list right now for something called vhost NVMe, but that's getting moved back and forth. We're not sure it's going to go anywhere. And creating a generic PCI offloading mechanism for QEMU is seeing a bit of resistance from the community because they are worried that people will just use QEMU as an infrastructure and write their own device implementations in user space, and then they're not contributing to open source anymore. So we came up with something really cunning on the KVM forum last week, which is to have an offloading protocol that is GPL. And the question is, how do you do a GPL protocol, right? That's tricky. And we based ourselves on something Apple did a while back. And I'm not going into details of what Apple did, but the GPL protocol can involve a handshake that exchanges a poem. For example, user space, open source is great, user space is awesome, and I'm a poem. It doesn't matter what it is, it just has to be a sentence. A poem can be copyrighted. And then you can copyright something that the protocol needs to exchange, and you add a license to QEMU saying, I grant this license to anyone else who is GPL, right? And then they can do it. Obviously, you can bypass it by have a stub application that is GPL, but which can talk a different protocol with like a dual license application. Or you can just modify QEMU to not have that handshake and then just distribute the open source, the source code of QEMU, which is valid GPL thing to do. But then there's a lot of shaming if you do that. You say, hi, you're not a good player. So whether this is something that is going to fly or not remains to be seen. Because there is a lot of interest from various industry people. For example, SPDK is dual license. So if we do that, SPDK cannot use this thing. And we wanted to use it because it's not about not improving the QEMU implementation. That's something I did not highlight. It's about having a single process in user space who can own a device and communicate with many virtual machines. And you cannot have that with QEMU because one QEMU manages one VM. So you need to have many QEMUs and one guy responsible for the storage and responsible for the data path of everyone. Now, whether that's safe is a different story, but yeah, that's the point. Any more questions? I'm the only thing standing between you and beer, I think. It's the problem of being the last presenter. 10 minutes? Oh. I have a lot of data that I can show that is fun. Sure, Paulo.
Yeah, so very impressive, really.
Thank you.
Congratulations. First, one observation. It looks like what you guys have done sort of removes the very motivation for block and queue because
no, not really, it doesn't. It doesn't because if your virtual machine wants to use the kernel, then you need block and queue for the VM. On those light blue graphs that I showed earlier, which are here, you could only, I may have pressed one too many, no. You can only scale like this if the VM is using block and queue. If you don't, then it doesn't matter how many CPUs you add to the VM, you're still stuck to 200-ish thousand IOPS.
But with your solution with SPDK also in the guest, it's only one process.
More or less. Applications, well, then yes, because you're not using the kernel, which means you're not using the block and queue implementation of the kernel.
Yeah. And you are extremely faster.
Sure, of course, yeah. I had this discussion with
one process.
Yeah, it is.
Wow.
It's correct. You're welcome to review my numbers. They're all very academic. I had this discussion with Hannes from SUSE at the Open Source Summit last week, and he's really keen on looking at ways to improve how kernel does polling to see if it helps. And one of the things we came up with is that today when the kernel polls, what the kernel does is submit some requests to the driver, and then if he has an idea of how long that's going to take, he goes to sleep, he wakes up, just sets up a timer, wakes up just before that, and then polls. But he polls only on the completion queue. And he doesn't poll on perhaps more things that could be coming in. So perhaps an improvement you can make is for that poller to actually poll on the submission queues as well, and maybe other things that could be coming from different processes. That may already make a difference.
You're right, because they tried polling, they measured that, they saw that it wasn't useful like 2 or 3 years ago, but it was exactly because of what you said, because they were polling only on one side.
Yeah.
Yeah.
On the Vault conference, the last one that happened, I think it was a couple of years ago, someone from Western Digital presented a lot of measurements on polling and hybrid polling. You were there? Okay. Boston, right? Yeah. Yeah, I was there too. Yeah, so that presentation is really good to get heads around polling. And I remember his conclusion was, there's still a few microseconds unaccounted for in a kernel, and I don't know where it's coming from. If you look at things like FIO versus PERF is one of the things I mentioned. And by the way, this is a more complete view of, sorry, let's try this one. This is a more complete view of what the four drives look like when you're doing I/O in the kernel. Before I only had a bar graph. This is the actual full story. You can see that this is a different class of CPU. These measurements were done a while back, so the numbers don't add up with the rest of the things I presented. But you can see that one CPU in the kernel is down here. Then 2, 3, 4, 5, 6, 7. You get to 12 CPUs in the kernel, you can get to the 2.4 million IOPS. When I used FIO, right, with the SPDK plugin in FIO, meaning FIO is using SPDK, one CPU could do about 1.3 million IOPS, 2 CPUs could get to 2.4 million IOPS. So FIO with SPDK plugin needed 2 cores. And I asked Intel, hold on, you said that SPDK can do like millions of IOPS per core. When I measured PERF, one car actually gets to 2.3 million ops and it's better. And they said, we promise you the code inside this plugin is the same, and PERF is just more efficient. They told me they spend a lot of time staring at assembly code and making sure that their loops fit into the instruction cache and things like that to make sure that's the difference he makes. That's like 1 million ops right there. And their code actually goes faster. If you have more drives, it goes beyond that. So with that, you can think that if you're going through the kernel and you have to switch your code between going through the block layer into a driver and work queues and things, there's no way you can make that optimized at that level. So with this, that's why I'm a true believer in user space stacks. But maybe you can load something in the kernel that drives the device and does this work too, like vhostnet style. That's how virtualised virtualization works in the kernel, right? So it does make a difference to care at that level. And that's why, for example, when we wrote Frodo, we were trying to take care of not allocating any memory dynamically. Everything is pre-allocated. The amount of we don't have locks anywhere. Our Datapath is lock-free. We created a system where we use coroutines to do different functions. And we created a coroutine scheduler that doesn't do system calls to change stacks. So we can actually change between logical components of our code without doing any system calls, which recently, thanks to security issues in modern processors, became an expensive thing to do, system calls, right? So avoiding system calls also makes a big difference, which perhaps is another problem with kernel data paths. I'm not sure if you can make the data. The idea is you want to stay in one side, right? If you need the data to come to user space, then try to do everything in user space, everything you can. If you need the data to be in the kernel, then try to stay in the kernel. Right? I'm not picking sides. I'm just saying don't cross the border that often. Right? That may be an answer to that.
And then I have my actual question.
Yeah.
So this works very well for I/O-bound workloads. Mm-hmm. But if you have a sort of intermittent workload, then how do you handle it? Because you have an on-off solution.
Yeah. Oracle gave a talk at the SPDK summit back in May where they discussed how they plan to, maybe it's also full of disclaimers, right? But they talked about how they're designing an SPDK solutions that can perhaps work with Oracle. And they had this design where they need to have different I/O threads inside of their application, which they have their own internal submission queue model to then get to a worker that is polling on the device. So it depends on the application. That's the answer to your question. And it needs to be thought through. And maybe that's another reason why virtualization is a good reason. Let the hypervisor do the hard thing for you. And if you really care about that, then you can do that in the VM. If you don't, then you don't care so much about it. Maybe if you're doing a lot of CPU work at the same time, you don't need 2.4 million IOPS, then you can go through the kernel and then you're fine, right? You're fine. You're spending a little bit more CPU there, but you're fine.
Okay, we have time for the last question.
Yes.
Thank you very much.
Hey.
It's maybe obvious, but did you test SSDs?
No more SSDs. Sorry.
Is the result such significant, the difference?
For no more SSDs.
Yeah.
I did measure, not with this prototype, but I have a bunch of measurements on NVMe drives that do not have 3D crosspoint. So just before I answer that, that's where SSD sits in the story, right? We came from mechanical drives, we ditched the moving parts, and that's basically what an SSD is, right? It's a hard drive that has some sort of a block controller that's ATA or SCSI or whatever it is, but it has flash memory, normally NAND. And then what happened is people realized that the buzz was low, so they've moved it closer to the CPU by putting the SSDs on top of PCIe, then moving that by removing the SAS, or in the case of 910, I think it was a SAS controller, but it's SCSI. And NVMe is just a standard based on that model. So the PCIe with solid state storage, if you remember Micron Fusion IO was a really popular one at the time. They had all these fast devices, these PCIe storage devices that needed proprietary drivers. So NVMe is just the standard to drive those guys. So what I do have is measurements on NVMe, not normal SSDs. And another important point is I'm hearing, I don't know, that there's a lot of demand by cloud providers for SSDs to have NVMe interfaces. Even normal SSD drives that perhaps sit down somewhere in the architecture of a motherboard, for them to provide an NVMe interface. Because NVMe is a much more efficient protocol. So you can think that's because it was designed for printers and scanners, right? It actually works for stuff like that. There's commands to detect whether the tray of a drive is open. NVMe is much leaner. So it may be the case that in the near future, maybe next year, maybe the year after, you'll be able to be using SPDK to drive SSDs. Right now, you can't really. But this is an interesting measurement that shows a normal NVMe drive with none memory, and that's a throughput graph. So you see the difference between that and the 3D crosspoints, that the S-curve for the 3D crosspoint is much more to the left, if you recall that. Otherwise, you can look at it later. But when you add 2 CPUs doing I/O, and 8, and 16, and 32, and 64, and 128, then you get to a point that you're not really coming to the left anymore. Your throughput doesn't increase because you're bound by the IOPS, essentially. You're doing small requests and you cannot do more requests. The number of requests you're doing on this left part of the graph is what bottlenecks, right? So you'd probably expect something similar for SSDs when they come around, but I don't have the exact data to show that. Time?
Okay, thank
Beers?
you. Yeah, you need to pick the best question.
Oh, that's difficult. What's what? I like at least a couple of questions really well, but I'm going to just follow suit what I've seen other presenters doing, and I'll give it to the first person who asked questions. Was that the logical volume one, if I remember right? Yep. Okay. First person who asked questions, got it. Yeah, lots of graphs. NUMA effect. Yeah, what happens when your FIO is attached to one core, another core. That's another interesting thing. SPDK doesn't suffer from NUMA effects, but I'm going to stop now.
What was the second
We're not going to go to the bar.
What was the second one?
Mediated devices, I think. That was interesting because not a lot of people know about mediated devices, so that was interesting. Okay, he doesn't get t-shirts?
He already got one. For
otherwise, Paolo as well had this is a technical draw here. So I guess they already have like half a dozen t-shirts each.
We're gonna have lightning talk session in this room.
Okay.
In 5 minutes.
Right. Thanks, everyone.